So what we're doing is we're evaluating proposed mechanisms, which are nothing more than individual elementary steps. And from all the steps of a process that gives us an entire reaction, what we're trying to do here is determine what the rate law would be from this proposed set of steps in a chemical overall reaction. And today what we're dealing with is a fast reversible equilibrium. And how do we handle such a proposed mechanism? So the first step is to look at this mechanism and understand that all of these individual elementary steps, this is step 1, step 2, step 3, and so far, okay, they should all collectively, okay, basically reduce or cancel out to the overall reaction. So let's do that first. And that could be a typical question where they give you a mechanism and say, what is the overall? Now, this is not Hess law. We don't have delta H's to manipulate. We're not going to manipulate and flip any of these questions. We're just going to see these are individual steps, okay, where intermediates are made that connect one step to another. And we'll talk more about that. But first, let's go after the skill of trying to cancel out all of the intermediates or all of the these compounds in these steps to give us the overall, a mechanism. And that's what this is. This is a mechanism, and a mechanism is nothing more than a step-by-step, okay, approach of how all individual elementary collisions, okay, or steps give us the overall. So let's go after it. So we're going to cancel some of these elements out, or these compounds. So I have H2 on this side, and I don't see any hydrogen. I see two hydrogens here. These are hydrogen atoms. So I would cancel those out. There's one. I need a second one. There's a second one. And then I have SO2, okay, and if I look, I don't see any SO2s on the product side, so that looks like that may be a reactant too. HSO2, that's an intermediate. And then we have HSO. We have two oxygens, and then we have two oxygens over here. All right, I have HS, and I have HS over here. And then I forgot to cancel that out for the two oxygens. I have O2, and I think I'm done. So what do I have is I have hydrogen that's left remaining, plus SO2, sulfur dioxide, okay, with my arrow. And I'm going to make oxygen and H2S. And so we canceled out all of the other chemicals that are not part of the overall reaction. All right, and sometimes they give the overall reaction and sometimes they don't, and they could say which is appropriate, what mechanism, and they'd have to cancel. Notice I didn't multiply by 2 through any of these, didn't have to flip any. This is not Hess law. Okay, this is just seeing if the overall steps to this reaction, okay, cancel out to give us that. It should, if it is. Now, this is a proposed mechanism. We can't watch these happen, okay, with a microscope. So this are proposed, and we're going to do a test, usually with some experimental evidence, to see if this set of steps supports this mechanism. Now, before we do so, we have to know what this mechanism, or this proposed group of steps for this overall reaction, what are, or what is the rate law that comes from this. Now, before I do so, I do want to make sure that we understand that we do have some intermediates. Now, what are intermediates? Intermediates are chemicals that are made in these individual elementary steps that link one step to the other. Notice hydrogen goes back and forth. It's a fast reversible equilibrium, but it makes this H2, or two hydrogen atoms. And this hydrogen atom links the second step to this other reactant. And then if you notice, another hydrogen, okay, is used to use up an HS. Now this second step produces HSO2, and this is again another link from one step to the other. Now keep in mind that these intermediates are highly reactive. Okay, they don't last very long. In the case of hydrogen, you have a hydrogen atom, which is like a free radical. It's got electrons sticking out. So hydrogen doesn't exist very long in that state, and it's very reactive. So these intermediates are highly reactive. Okay, and that's why once they're made, they usually react to the second step. Here's a intermediate, here's the other one. Here's some oxygen that links what? To that step. This one will link to that step. This hydrogen here, hydrogen sulfide, okay, or HS I should say, links to this, all right? So all of these intermediates link the ending of a step to another. They do so because they're highly reactive. As soon as they're made, okay, they react. And that's why you notice all of these steps here are very fast. Now you may say, well, Mr. Grodsky, wait a minute. An intermediate is made from the first step. So why is this the slow step? And they're giving this to you that this is the slowest step. Okay, but we should be able to figure that out, and I want to go over this now. Okay, now before we do so, understand that there are no catalysts. A catalyst would be on the reactant side and reproduced somewhere, and there's no catalyst here. But let's just talk about why this is the slowest step and what this fast reversible, okay, step does to this mechanism and how we have to handle it a little differently. First and foremost, we have hydrogen molecules, H2. They are bonded and very stable. Okay, and they're sharing two electrons fill the first energy level, and they become what? Free hydrogen atoms, which are highly reactive, which means as soon as I make this H2 into two atoms, the two of these go back. As soon as this breaks apart, it goes back. Now, it probably takes a time to wait for this to break apart, but as soon as this breaks apart, this goes back. As soon as this breaks apart, it goes back. Why? Because the intermediates are right next to each other and they're highly reactive. So a lot of the hydrogen that breaks apart as two H's jumps back to make the more stable H2. And that's why they call it a fast reversible. As soon as I make these two products, as soon as hydrogen, which is one particle, breaks apart into the two hydrogens, atoms, they're going to quickly what? Collide and reform because they're so highly reactive, they're not going to stay around, okay? And so they quickly go back. So as fast as this goes back, and that's why it's a fast equilibrium. Now the second step, again, is made up of this hydrogen, meaning what? Well, what's really happening in the second step, what we have is we have SO2 molecule that's looking to collide with one of these hydrogens. Okay, so think about that. This SO2 is looking to collide with one of these. Now it's bouncing around the beaker or whatever, the reaction vessel, but because most of this, once it's made by the breaking down of the H2, reforms the H2, you really have to wait for a chance event for SO2 to collide to an available H. Atom. What I mean by that is this breaks apart into two. These are so reactive, they're going to react back together to reform that. This arbitrary molecule, S2, has to collide with this H2 probably as it's being made before it reacts with this other H. And if you think about that, if SO2 has to collide with the H probably as it's being produced, that event is going not to be a fast event. We have to wait for the chance event to SO2 to bang around and just hit one of these as it's being made. And that's what makes it a slowest step. So the second step after a fast equilibrium is going to be the slowest step in all of these steps here. Yes, it has a fast reactive intermediate with that one electron that once this collides with the H, we make another intermediate which is going to react and break down, in this case, by itself. So the point is that we have to wait for the chance event of an SO2 to hit this H just as it's being made before it goes back, and that's what makes it the slowest step. So the slowest step after a fast reversible equilibrium first step, always the slowest step. And as you guys should understand, this slowest step in a group of elementary steps is the rate determining step. Rate determining. That is important. It's the slowest step in all of these steps, which means the entire process of making this chemical from all these steps goes as fast as the slowest step. Okay, it's the weakest link. We're as strong as our weakest link. So all of these go pretty fast, but the slowest step is what determines the speed of the entire process. I get out of my house as a family as fast as my wife can lead. So we don't get anywhere until my wife leaves. So that would be my rate determining step, okay, in terms of speed of leaving the house to go somewhere. All right. Now, so let's continue. So now that we know the elementary step, and you should understand this, if I've just found the elementary step that's responsible for the speed of the entire process, called the rate determining step, I can write my rate law. Rate, which is how fast the reaction goes, is equal to the constant, which is the rate law constant for the entire reaction, times the individual concentrations. Now, when we write a rate law, we write a rate law for the actual reactants that we use. All of these other, whatever colors these are, I'm colorblind, so I think there might be, I don't know, purple, but all these other colored purple spheres, we'll call them, represent intermediates that are made from our what? Okay, from our reactants, okay, or from the step going in the forward and connecting. So we can't write and put any intermediates into our rate law because they react so fast, you can't measure them. All right, they're so unstable. So we have to put reactants or products into our rate law. Now, I do know that SO2 is one of my what? One of my reactants. And I do know, because it's an elementary step, there's a coefficient of 1 in front of the SO2. So that becomes an order of 1. Coefficients become the orders only if you have an elementary step. In this proposed mechanism, based upon the fast equilibrium, as we just discussed, this must be the slowest step. Individual elementary step, so that means that 1 for the SO2 goes there. The question is, what do I put for H2? There is no H2 in this step. We only have hydrogen. So I have something that is not good. I have H, okay? And so I have H that goes here. And it would be for the 1 power H. But this is bad because guess what? This is an intermediate. And we can't have intermediates in my rate law because I can't measure it. It reacts too fast. So I can never use it to determine the initial rate of the reaction. Okay, so what we're going to do, party people, is we're going to we're going to solve for the other reactant using the fast equilibrium. Okay, now let me explain. In our first step, I'm going to rewrite this. I have H2 becoming 2H. That's important, or as I like to say, impertinent. Okay, it's equilibrium, double arrow, although I have the 2 arrows going the same way. All right, here we go. So here's our double arrow. Okay. Now the second step is this H combines with an SO2 by chance that we have to wait for because, gosh darn it, these two H's with the 1 electron react back very quickly, makes our another intermediate, but we don't really care about that. Now, what I'm going to say is, boy, can I relate, and we can, that's kind of rhetorical, can I relate this H back to this reactant? Remember, H2 is a reactant, not an H. We have to put the reactant. Well, hello, because of fast equilibrium, okay, and because it's the slowest step, this slowest step was waiting for an H to be available so that SO2 can collide with it. So what I can do is, because the fast equilibrium, okay, produces the H that this needs, I know something about equilibrium, and that means that the rate of the forward equals the rate of the reverse. So watch what I do here. Okay, for the forward reaction of the first step, I just rewrote these steps here so I can write them here. I know that the R, the rate of the first step, equals K of the forward times H2 to the 1, which equals what? The reverse is R of the reverse, which is equal to the what? Um, the constant here, which is constant of the reverse, okay? It's the rate law constant, I can say that. And that, of course, is what? H to the second order, because the coefficient is 2. These rates are equal, okay? Now, what I want to do is I want to solve for the H, okay? Why? Because if I have its equivalent, I can put that right in here. So let's solve for the H, okay? H to the second order, which I got because of this coefficient in the reverse, and I'm going to divide by KR equals H2. I have the K rate law constant of the forward divided by the rate law constant in the reverse. I'm just doing algebra. And then the next step in the process here is get rid of my square root. Okay, so I square root this side, I square root this side, and what I get is, I get, well, square root of 2, of course, is h, and that's what we wanted. Hey, that's what we want here, is equivalent to the square root of h2. Now, the square root, party people, of h2 is, if you didn't already know, is h2 to the 1/2 power. The square root is actually is basically an exponent to the half power. And then of course I have the what? So let's write this out. H, I didn't have the room, is equal to h2 to the 1/2 power, because that's what the square root is of that. And then of course I have the square root of this ugly, the what? Rate law constant of the forward divided by the rate law constant of the reverse. And so party people, what I'm going to do is I'm going to put this entire expression for what? For h. I'm going to put that right into, okay, where we're trying to solve for what? There. So I'm just kind of, sorry, I'm going to put that right here. And so when I rewrite this, okay, when I write this, and of course, I want to get rid of the rate determining step there. It makes some room here. So when I rewrite this, what I got is the rate law constant is equal to, and I'll put this in a different color, square root of k of the forward divided by the what? The rate law constant of the reverse. Okay, that's what this expression is. I'm doing it right here. Times a hydrogen to the 1/2. And that goes to the 1/2 power. Okay, remember I'm just putting this expression here for my h, and then of course I times it by, I'll put it in blue because I can do that, and I'm going to go to the SO2, and that's to the 1. So this looks pretty nasty. Now don't forget that I have a what? I have a k here too, so I got to put that k in here. Now I want to tell you, party people, that looks pretty nasty, but when you think about it for a second, the k for the second step times the square root of the what? K for the forward over the k of the reverse. This entire product of these k's actually equal to the, guess what? The entire reactions k. So R is equal to that, who cares what it is, that equals to the entire reactions rate law constant. And now you have H2 to the 1/2. And notice we related what? H to one of the reactants, to the SO2 to the 1. And party people, there is your rate law for fast equilibrium. So this rate law that we just found represents the rate law for this reaction using this series of steps, using this mechanism. Okay, it's important that you realize that this fast equilibrium gave us the opportunity to work backwards and find an equivalent for what? An intermediate. Remember, this is an intermediate here. Okay, this is an intermediate. If we color it the same way as my other intermediates, okay, remember intermediates are nothing more than really very fast reactive chemicals made from one step at least prior. And so they connect one step of a elementary step to another in a mechanism. So initially when we wrote this, this was the intermediate, and we can't have that in a rate law. So what I'm going to do is I'm going to kind of rewrite this a little bit to make sure that you can clearly see what we're saying here. Okay, so again, a last little ditched effort here for you to understand, okay, is that I essentially put this equivalent, this algebraic equivalent for the H, okay? And so I solved for the H, and remember I did so because the rate of the forward reaction equals the rate of the reverse. Okay, that's the first thing in fast equilibrium, all right, or reversible. Because of that, the forward reaction equals the reverse, and therefore by setting the rates equal, and that's what I did right here. This is the rate of the forward reaction, and this is the rate of the reverse of the first step. And the reason why there's a 2 here is because there was what? two H's in the first step. Okay, and there's only one H, one in the second, because this is a what? Elementary step. I'm allowed to do that. So this is what I did. And then I said, okay, I'm going to divide by the my rate law constant of the reverse. That's why I went to the bottom. That's K of the R. Then I did the what? Square root to get rid of the 2, and I square root both sides. Okay, and so that's what I have. And so, okay, so the square root, okay, if you very carefully, the square root of a number, okay, that's like just 1 here is really a 1/2, and that's what we got to the 1/2. And this, of course, is what we have here, and that's what we came up with. And then we did what with that? We plugged that in into the rate law, okay, for the second. Why? Because it was the slowest step. So I plugged that back in, and because this equals h to the 1, and I found an equivalent, okay, using setting the rates equal, I just plugged that back in, okay? And of course, that gives me this incredibly complex, hey, this is the k of the second step elementary. This is the square root of the division of the first step forward k over the reverse. And when you multiply this together, if you had the numbers, that would give you the reactions k. Okay, that's important. And then, of course, there you go. So the rate law for this overall reaction based on this mechanism that has a fast equilibrium is R is equal to the reactions K, which we now know is this value times the what? The second steps K, but it doesn't matter. It's the reactions, overall reactions rate law constant, times a reactant, okay, has to be in the rate law, not intermediate, to the half, okay, times SO2. And SO2 to the 1 we got from the what? We got that from right from the second step. And there's a 1 in front, so that's where that came from. All right. Now, if you think with me for a second, just stay with me. I'm trying to fight through this so you understand. We're relating this intermediate to what? This reactant. And I can do that if the fast equilibrium is above the slowest step, which it normally is. All right. Now, to relate this, this is 2H, but I only have H here. 2H really is equivalent to the H2, but I only need one of them. So if 2 H's is equivalent to an H2, and I want to relate it to 1H, one of these should be equal to what? This to the half power. And that's how it works. Okay? So what I would like you to do is try to find what the rate law would be for the proposed mechanism for this overall reaction. Okay? And so stop me now and try to find what the rate law, this is a fast equilibrium. Okay, this is the slowest step. All right, and so stop me now, and when I'm ready to run, I can show you how to do it, so stop me now. All right, I didn't want to do all of it because I wanted you to be able to see me do some of it. So in evaluating this, first and foremost, I must make sure that this reaction, okay, these steps do cancel out to give me 2NO, give me this entire reaction. So notice I have 2 NOs, that gives me the 2. Notice we have BR, and notice what cancels. This would cancel because it's an intermediate. It's found on both sides of each arrow, and therefore it's gone. It's not part of the reaction in terms of the rate law, although it's an important part of this proposed mechanism. Remember, this is a proposed mechanism for this reaction. We're trying to see, and people propose this because they think that the rate law will be something. So what is the rate law that they think this will be if they're using a fast equilibrium for the first step? The first thing I realize is the slowest step is the second step in fast equilibrium, because if remember, NO plus BR produces this. This is so what? Reactive, it goes backwards. It breaks down. It's so unstable, this goes backwards. However, if by chance an NO collides with it before it goes back, okay, and of course that's going to be slower than this going back, this is the slowest step. So I know my rate law is based upon the second elementary step, which means the coefficients become exponents. Look at the NO, it goes to the first. This is the rate is the K of the second step, and this is my NOBR. Now, there's a problem. I cannot relate my rate law. Remember, rate law is about the initial concentration of my reactants. My reactants are NO and BR. Hey, That's not one of my initial reactants. I can't measure this because it's something that is made very quickly and used up very quickly. That's how intermediates work. So how do I relate it? Well, if it's fast equilibrium, I can connect this back to the one of my reactants. So what we do is say the rate of the forward reaction equals the rate of the reverse. And why I have an F there is beyond me. So I'm glad we did this. So this is the rate of the reverse first step. So what's the rate law for the first step? Well, it's going to be K, okay, rate law constant for the first step of the forward, so F to the 1. And it's going to be what? NO. And it's going to be BR. And both of these to the first power because there's a coefficient. All right. And that has to equal to the K of the reverse of the first step, and that's going to be what? NOBR to the first power. Well, let's relate it to NOBR, right? So I'm going to divide by, so the next step is going to be NOBR, and I'm going to divide by my rate law constant for the reverse, so it's going to be K of F to the 1 over K R of the 1 times this expression here, which I'm not giving myself enough space, NO and BR. Okay, and I just solve for it. All right, so that's what we have here. So let's continue on. So let's clean this up. We have our NO, BR can be expressed because of the fast equilibrium to the following. Let's make this in red. Okay, it's going to be K of F of 1 over K of R of 1, and it's going to be times the NO BR. So plug this in, okay, right here. And what you get is you're going to get K2, which is the second step's rate law constant, times the rate law constant of the forward first step divided by the rate law constant of the reverse first step times the concentration of NO times BR, and that's what this gave me. So let's make sure we understand that I interjected, or I put this in. So all of this is for BR. Okay, and then of course I still have what's there is I still have what is part of the elementary step of the slowest step, second two. I have this to the first. And we can simplify this. As I said before, the K, rate law constant of the second step, times this fraction of rate law constants of the forward and reverse, that's going to equal the rate law constant of the reaction. So the R of the reaction is, that's going to be a K. I'm not sure why I'm going R there, thinking R. So that becomes K, all right, of the entire reaction. Hey, there's two of these. So this is going to become NO to the second power and BR to the first. And that is our rate law. This is the rate law from this proposed mechanism. Now notice something, party people. Some people might say, well, wait a minute, the coefficients that you deduced from this fast equilibrium, hey, is a 2 there and a 1 for the BR, are equal to the coefficients. Doesn't this mean that the coefficient of 2 here and a coefficient of 1 here, I know it's not there, equals the same rate law? Doesn't that really suggest that this happens in one step? Well, as I said before, having two NO molecules come together and collide with a BR molecule, so this one is here, this one collides, the chance of a thermomolecular reaction is so small. So this type of mechanism tries to explain how this could happen. So the chance of three particles, two NOs, all right, nitrous oxides, and one Br2, the chance of them all colliding at the same time is very minimal. So this is a mechanism to try to explain that it probably occurs in two steps, all right? In any case, the proposed mechanism, based upon the work we just did, is as follows. And this is what you could use now to be tested against, of course, with experimental evidence. And of course, this entire order of reaction is third order. All right, so hope that helped. My key is probably a lot neater than me doing it live, and any of the following that helps you, great. See you later.